Okay, so
Yeah.
let's unpack this. I spent the morning staring at this stack of documents you sent over.
Uh-huh, yeah.
And I have to be honest, at first glance, it looks less like a tech briefing and, more like a syllabus for a grad school seminar on computer science history.
It does look a bit heavy on the Greek letters and formulas when you fan it all out, I'll give you that.
It really does.
Yeah.
But once I started actually reading the titles, the dates, I realized what we're doing here. We aren't just doing a deep dive into crypto or blockchain in the way
Yeah.
people usually talk about it.
The prices, the coins, the height.
Exactly. This is a genealogy.
That is the best way to frame it, a genealogy of digital trust.
So our mission today is to trace that lineage.
Yeah.
We're going to span exactly 40 years. From 1976 bell-bottoms, disco, mainframes the size of a room,
Right.
all the way to 2016. We're going to see how we went from these theoretical math problems scribbled on chalkboards to a world computer running on a global network.
And most people have this misconception that the story starts in 2008 with the Bitcoin white paper.
Right.
But if you look at the source material we have, Bitcoin is really the third act of the play. The concepts of mining, of digital scarcity, of privacy. These weren't invented by Satoshi Nakamoto. They were being fiercely debated in academic halls decades before anyone mined a single block.
That is the part that really surprised me. It's like finding out the smartphone was actually invented in pieces back in the 1950s.
Okay.
So let's rewind the tape. We're starting in what our notes call the Foundation era. The year is 1976.
1976 is the watershed moment. This is where modern cryptography essentially wakes up. We're looking at a paper called New Directions in Cryptography by Whitfield Diffie and Martin Hellman.
Diffie-Hellman.
Oh.
I feel like I've seen that hyphenated name buried in the settings of my web browser or maybe secure messaging apps.
You definitely have. It's ubiquitous. But you have to understand the world before this paper. Before 1976, if you and I wanted to send a secret code to each other, we had a logistical nightmare.
Okay.
We had to meet in person first to agree on the key. If we were in different countries, we'd need a trusted courier. You know, the whole briefcase handcuffed to the wrist thing. This was called the key distribution problem.
Because if we try to agree on a key over the phone and someone is tapping the line.
They have the key too. Game over.
Okay.
Precisely. The system was symmetric. The key that locks the box is the exact same key that opens it. Diffie and Hellman proposed this radical shift. Asymmetric cryptography. They mathematically proved you could have two keys.
Two keys.
A public key that you can shout from the rooftops and a private key that you keep absolutely secret.
So I can send you a message locked with your public key.
And only my private key can open it. Even you, the sender, you couldn't unlock it again if you wanted to.
Wow.
This meant two people who had never met could communicate securely over an insecure channel. It shifted trust from, physical couriers to pure mathematics.
That's a massive unlock for a digital world. But then, just 2 years later, in 1978, we get another famous acronym, RSA.
Rivest, Shamir, and Adelman. They took the baton and just ran with it. Their paper, A Method for Obtaining Digital Signatures and Public Key Crypto Systems, it solved the other half of the trust equation.
Which is?
Identity. Authentication, exactly.
Yeah.
Diffie-Hellman let us hide the message, but how do I know the message actually came from you?
Right.
In the physical world, you sign a document with ink, but ink can be forged. RSA introduced the digital signature.
I want to pause on that because we use that term so loosely today. When I digitally sign a PDF, I'm usually just pasting a JPEG of my handwriting.
Right, yeah.
That's not what they meant in 1978, is it?
Not at all. That JPEG is meaningless, securely speaking. An RSA digital signature is a mathematical proof. You use your private key to sign the data. If I have your public key, the math allows me to verify two things instantly.
Okay, well,
First, that only you could have created the signature, and second, that the document hasn't been changed by even a single byte since you signed it.
so it's like a wax seal. But if someone tries to peel it off or even just change one word in the letter, the seal just explodes.
That's a vivid way to put it. If the data is altered, the math simply fails to compute. The seal breaks. So by 1978, we have privacy and we have authentication.
We're building the toolkit. But then we hit 1979, and we get a concept that feels a bit more abstract. The Merkle tree by Ralph Merkle.
Ralph Merkle is one of the unsung heroes here. He was actually working on public key crypto around the same time as Diffie and Hellman, but in '79 he published this work on integrity proofs.
The name Merkle tree always makes me think of botany, but the diagram in the source looks more like an upside-down root system. What problem was he trying to solve?
Scalability and efficiency. Imagine you have a massive database, so say a million transactions. If I want to verify that one of those transactions is correct, traditionally, I might have to download and check the entire database.
Which is slow and heavy.
It's impossibly slow. It would kill any global network before it even started. Merkle figured out a way to hash or fingerprint pairs of data, then fingerprint those results and so on, building up to a single master fingerprint at the top. The root hash.
So the top of the tree represents everything below it.
Everything. And here's the magic. If you want to prove to me that one specific transaction exists in that massive list, you don't send me the whole list.
What do you send?
You just send me the tiny path from that one transaction all the way up to the root. I can verify it instantly.
That explains how modern blockchains can even run on a laptop. You don't need to store the whole history of the world to know what's true.
Exactly. Without Merkle trees, a system like Bitcoin would require industrial-grade servers for every single user. It would be totally centralized. Merkle gave us the efficiency to be decentralized.
Okay, so we have privacy, signatures, and efficient data structures. Now I want to jump to 1985 because this is one of the coolest, most sci-fi concepts in the whole stack.
Ah, yes.
Zero-knowledge proofs.
Goldwasser, Macaulay, and Rakoff. This paper, The Knowledge Complexity of Interactive Proof Systems, is a heavy read, but the concept itself is. It's beautiful.
The name itself is a paradox.
Yeah.
How can a proof offer zero knowledge?
It's about the knowledge gained by the person verifying. It's the ability for me to prove to you that I know a secret.
Okay.
Without revealing the secret itself and without revealing any other information about it.
The classic analogy is the cave, right? The Alibaba
And
cave.
it is, but let's make it more practical for the digital age. Imagine a website requires you to be over 21 to enter.
Mm-hmm.
Currently, you have to upload your driver's license. You are proving your age, yes, but you're also revealing your name, your address, your license number. You're revealing everything just to prove one thing.
Which is a privacy nightmare.
A zero-knowledge proof lets you mathematically prove I am over 21 without sharing your birth date or your name or your ID. The website just gets a true or false confirmation. Nothing else.
That is incredibly powerful. And this was 1985.
1985. But here's the catch. It was computationally very, very expensive. It was brilliant theory, but computers back then were struggling to run spreadsheets. Doing these complex cryptographic proofs for every little interaction was just impossible. So it sat on the shelf.
A tool waiting for a job. We'll put a pin in that for later.
Yeah.
So that wraps up the foundation era. We have the math. We have the plumbing things like PKI in 88 and MD5 hashing in 92.
Yep.
Now let's move to part two. The pre-blockchain era. The late 90s, the internet is booming, and the cypherpunks are starting to ask, can we use all this math to make money?
This is the era of experimentation and, frankly, failure. People forget that before Bitcoin, there were dozens of attempts to create digital cash. They all failed, but they all added a piece to the puzzle.
And it starts with a problem you wouldn't expect.
Spam.
Junk email.
In 1997, Adam Back released something called Hashcash. He wasn't trying to build a currency, not at first. He was trying to stop denial of service attacks and email spam.
How does crypto stop spam?
By adding a cost. The reason spam exists is that sending an email is effectively free. If I send one, costs me nothing. If I send 1 billion, costs me nothing. Adam Back realized that to stop the abuse, you need to make the sender pay.
But not with dollars.
Not with dollars. With computation.
You force their computer to do work.
Right. Hashcash forced the sender's computer to solve a tiny math puzzle before the email would be accepted. For you and me sending one email, that half-second delay is unnoticeable.
But for a scammer sending 10 million emails.
That half-second adds up to years of processing time. It becomes economically unviable to spam.
And that introduced the concept of proof of work.
The idea that digital data can have a physical cost attached to it, electricity and time, this is the direct ancestor of Bitcoin mining.
So that's 1997. Then 1998 seems like the year everyone tried to turn this work into money. We have two big proposals here. B-Money by Wade-I and BitGold by Nick Szabo. These are often lumped together, but they were trying to do different things, weren't they?
They were tackling different sides of the same mountain. When Dai's B-Money was focused on the consensus mechanism, how do we all agree? He proposed a system where every participant maintained their own separate database of account balances.
A decentralized ledger.
A vision of one, yeah. Trying to solve how we all agree on who owns what without a central bank.
And Nick Szabo's BitGold.
Szabo was obsessed with the economics. He actually coined the term smart contracts. But with BitGold, he was focusing on unforgeable costliness. He looked at gold in the real world and asked, why is this valuable?
Because it's scarce, and it's hard to dig up.
Exactly, you can't just print gold. Szabo wanted to replicate that in the digital world using Adamac's proof of work. He theorized that if you created a string of bits that required a huge amount of computational energy to produce, those bits would have value because they were scarce and costly to create.
So let's look at the board in 1998. We have Adamac's work to prevent spam. We have Wei Dai's decentralized ledger. We have Nick Szabo's digital scarcity. It feels like the car is fully assembled in the garage. Why didn't they turn the key?
They were missing the spark plug. The problem was, even with these ideas, they couldn't solve the double spend problem in a purely peer-to-peer way.
Right. If I have a digital coin, what stops me from sending it to you? And then sending a copy of that same coin to someone else instantly.
In the physical world, if I give you $1, I don't have it anymore.
But in the digital world, I still have the file.
Right. And to prevent that, every previous system needed a central administrator, a mint or a bank, to keep the official list and say, nope, he already spent that. Dai and Szabo couldn't quite figure out how to automate that administrator away.
Which brings us to part 3, the blockchain era. The year is 2008. The global financial system is collapsing. Lehman Brothers is falling. And quietly, on a cryptography mailing list, a paper appears.
Bitcoin, a peer-to-peer electronic cash system.
Enter Satoshi Nakamoto.
And this is the genius of that paper. Satoshi didn't invent a new form of cryptography. There is very little new math in the Bitcoin white paper. It's an assembly job.
An assembly job.
Satoshi took Merkle trees from 1979 for organization. He took Hashcash from 1997 for the mining. He took public key signatures from 1978 for identity. And he combined them into a system where the mining essentially secures the ledger.
That's the Nakamoto consensus.
Yes. By chaining blocks of transactions together using that expensive proof of work, Satoshi made it so that if you wanted to double spend, if you wanted to rewrite history,
you'd have to do all that work again.
All the work that the entire rest of the network had already done.
Which is economically impossible.
Exactly. He aligned the incentives. It became more profitable to play by the rules and mine new coins than to try and cheat the system. That was the breakthrough.
So 2009, the Genesis block is mined. Hal Furry, a legend in this space, receives the first transaction. The theory becomes a living network. But the evolution doesn't stop with digital cash. Our timeline jumps to 2013, and a young programmer named Vitalik Buterin.
Vitalik looked at Bitcoin and he saw a calculator. A pocket calculator is amazing. It does math perfectly. But you can't install Angry Birds on a calculator.
Right.
You can't write a Word document on it. It's single purpose.
And he wanted a smartphone.
He wanted a world computer. His white paper for Ethereum proposed a blockchain that didn't just track money, it could run code. This is where smart contracts become reality.
We mentioned Szabo coined that term, but Vitalik implemented it. How do you explain a smart contract to someone who thinks a contract is just, a stack of paper lawyers sign?
Think of it as a vending machine. A vending machine is a physical smart contract. The logic is hard-coded.
Okay.
If money equals $2 and deselection equals B4, then release Snickers bar.
Yeah.
You don't need a cashier to verify it. The machine enforces the deal.
So Ethereum allows developers to build vending machines for anything. Loans, insurance, voting.
Anything that can be expressed in logic. Ethereum manages the state of the computer. It moved the technology from programmable money to programmable anything. That launched in 2015.
Now, I want to close the loop on something we started with. We talked about that 1985 paper on zero-knowledge proofs.
Yeah.
The ability to prove something without revealing it. It sat on the shelf for decades.
This is one of my favorite connections. The issue with Bitcoin and Ethereum is that they are radically transparent. If you know my public address, you can see every single transaction I've ever made.
It's like posting your bank statement on Twitter.
Exactly. Which is terrible for privacy.
Right.
So in 2016, we get the launch of Zcash, spearheaded by Zuko Wilcox. Zcash was the spiritual successor to that 1985 Goldwasser paper. They figured out how to implement zero-knowledge proofs into a blockchain.
So they finally found the killer app for that 30-year-old math.
They did. Zcash allows you to send a transaction on a public blockchain where the sender, the receiver, and the amount are all encrypted and visible. But the network can still mathematically verify that the money exists and wasn't double spent.
That feels like magic. Proving a transaction happened without seeing the who, the what, or the how much.
It connects the dots perfectly. We started in 1976 trying to get two people to talk privately. By 2016, we had a global, decentralized financial network that could facilitate private value transfer without any intermediaries at all.
It really is amazing when you step back and look at the whole timeline. 1976 to 2016, 40 years.
Mm.
We had Diffie and Hellman just trying to replace a courier with a briefcase. Ralph Merkle just trying to organize a database. Adam Back just trying to stop spam.
And none of them realized they were building the chassis, the engine, and the wheels of a completely new economic vehicle. That's the beauty of this deep dive. New technology is almost never entirely new.
Right.
It's a synthesis. It's a clever recombination of old ideas that were just waiting for the right moment or the right hardware to click together.
It makes you wonder about the lag time.
That's the big takeaway for me. The idea lag.
Right. I mean, look at the gap we just discussed. Zero knowledge proofs, 1985. Zcash, 2016. That is 31 years. A brilliant idea sat there for 3 decades before it changed the world.
It's a sobering thought. We are often so obsessed with the now, the frantic news cycle, the latest token launch.
Yeah.
But the real structural breakthroughs are slow burns. They take decades to mature.
It raises a provocative question to leave our listeners with today. If the foundation of the 2016 crypto economy was published in some dusty academic journal in 1985, what obscure, dense, unreadable academic paper is being published right now, today, that nobody is paying attention to?
The paper that seems purely theoretical, maybe useless, maybe it solves a problem we don't even know we have yet.
Exactly. What paper from 2026 is going to be the foundation of the global economy in the year 2060? We might be ignoring the next internet or the next Bitcoin just because we don't understand the math yet.
That's the thrill of it. The future is probably already written. It's just sitting in a PDF somewhere that only 10 people have downloaded.
I love that. Well, thank you for taking this journey through the history of code and value with us. It's been a fascinating ride from the chalkboard to the blockchain.
It was a pleasure. I always get to look back to see where we're going.
And thank you to everyone listening. Keep looking for those hidden gems, and we'll see you on the next deep dive.